Okay, so now we move on to the 5th page of the worksheet. So what we're going to do now is try to describe how to analyze the function without not using the graph, but using the formula of the function. So the first thing we want to remember is that because a rational function is basically just a fraction, the domain for these kinds of function is going to be all real numbers except when the denominator cannot be equal to 0. Okay, so what should we look for in terms of the asymptotes? So first of all, when we're trying to find the horizontal asymptotes, essentially what we're going to do is to compare the degree of the numerator versus the degree of the denominator. So if you remember, the degree is the highest power. Right, so numerator is just what's on top, and denominator is what's on the bottom. So the reason we compare the degrees is because when we're looking at the horizontal asymptotes, what that means is that x is going to plus or minus infinity, and what this means is that x is taking on very, very large either positive values or negative values, and when the x values are large, basically what happens is the highest power is what controls the behavior of the function. And so that's why we look at the highest power on the top and on the bottom. Okay, so basically what you do is you just compare the highest power on the top and the bottom, and whether the degree on the top is bigger than the degree on the bottom, it's smaller than, or if they're the same, then you determine the horizontal in these ways. So if the degree on the top is bigger than the bottom, there's no horizontal asymptote. If the degree on the top is smaller than the degree on the bottom, that means the horizontal asymptote has to be y equals 0. And if the degree on the top is the same as the degree on the bottom, then we calculate the horizontal asymptote by taking the leading coefficient on top and dividing the leading coefficient on the bottom. So this is what we're looking for the horizontal asymptote. There's actually another case where you have a slant asymptote, but we probably don't have to worry about this case. Okay, so what about the vertical asymptotes? Well, basically the vertical asymptotes are where the fraction is undefined but because a rational function is a fraction is undefined when the denominator is equal to 0. And that's essentially how we're going to find the vertical asymptotes. So basically what you do is you completely factor both the top and the bottom, cancel out any common factors, because that's a different situation where you have removable discontinuities. So ignoring the common factors, the factors on the bottom that are left over after cancellation give the vertical asymptotes. And as always, if a factor looks like this, we write it as x equals a, like this. So for example, so if the factor is x plus 3, the vertical asymptote you write as x equals minus 3, right? So it's always the opposite. And for removable discontinuities, so they basically coming from the common factors, right? So the removable discontinuity are the common factors. on the top and the bottom, and if the multiplicity on top is bigger than or equal to the multiplicity on the bottom, then these factors have a whole at x equals a. Again, the same conversion. If the factor looks like this, the whole is like this. Common factor. The common factor is, say, x minus 6. The whole, we get x equals 6. And then finally, for x-intercepts and y-intercepts, this is similar to what we've always done. Right, so for x-intercepts, you just set the top equal to 0, and then solve for x. So just set the top equal to 0, because for a fraction, the fraction is equal to 0 when the top is equal to 0. And then for the y-intercept, you set x equal to 0 and calculate.